So we've demonstrated that we can actually solve these systems where we have two variables and a single equality constraint. And we did that by forming the Lagrangian. Well, we can generalize this to many variables and many constraints. So consider the problem maximize f of x1 up to xn now, subject to CH, we'll say this is the constraint space, x equals x1 up to xn, such that h1 of x is equal to c1 all the way up to hm of x is equal to cm. We want to do that, and we want to do it using essentially a Lagrangian. We want to generalize that idea because that was a very convenient thing, right? We suddenly were able to turn this very complicated constrained optimization problem into a normal unconstrained optimization problem where perhaps we introduced a few more variables or one more variable. So now we're going to introduce several variables, and we need to know when this is okay. So first, we must generalize the constraint qualification. So we have to know, so remember the constraint qualification was that our gradient can't vanish of the constraint function. But now we have several constraint functions, and so we need to figure out what should be done. Well, the natural thing, or the natural generalization, is, well, we still, if there was just one constraint, right, we just say the gradient of h does not equal 0 for a single constraint. And dh, we'll call it capital H of x star equals, so the Jacobian of the system of constraints So we form this Jacobian, and we evaluate it at all the critical point. Well, the generalization must have rank equal number of rows. And so the Jacobian of my constraint functions at the maximum is onto, is another way to say that. That's how we generalize this, and we're going to call this the non-degenerate constraint qualification. Or the NDCQ. And this will allow us to actually get good behavior for our Lagrangian. So now we generalize the Lagrangian. Theorem. Let f h1 all the way up to hm be C1 functions of n variables consider the program maximize f subject to ch x such that hi of x is equal to ai for all I. Now suppose x star in ch is a local max or min of f on ch. Then there are Lagrange multipliers mu1 star up to mu m star, one for each function h, such that well, I'm jumping ahead a little bit here. So we actually also want to have, so scratch this, we'll jump ahead. So suppose that this holds and h equal to h1 hm satisfies the NDCQ at x star. Then there are Lagrange multipliers mu1 star up to mu m star, such that x1 star all the way up to xn star, mu1 star up to mu m star, this point is a critical point of the Lagrangian. And now we see the Lagrangian in its full form. L of x mu is now a vector of Lagrange multipliers, is equal to f of x minus the first Lagrange multiplier times the constraint condition, x minus a1 minus mu2 h2 x minus a2 minus all the way up to mu m hm at x minus am. And that's the full form, and we're going to see an application of this full form in the next video.